Right, welcome back to Digital Electronics, Lecture 16. Alright, we're in Unit 2, Section 2 here. We are going to learn about truth tables and logic expressions. Now, we've gone over some of this in class already, just, doing some basics as we put some basic tables up. But we're going to get into it a little bit more, alright, and be able to start producing some Boolean expressions out of this, okay? So we're going to learn how to properly construct a truth table, and we've gone over that a little bit in class, but knowing what the pattern is, such as 0, 0, 0, 1, 1, 0, 1, 1, and then how we add on to that, we're going to get into and understand how how to write the Boolean expressions or the logic expressions, okay, what we call the minterms, from the output, okay? So we're going to write an SOP, a sum of products, okay? Or we're going to go backwards. I'm going to give you the logic expression, and you can create the truth table for me as well, okay? So keep in mind, SOP, sum of products, okay? Sum meaning to add, and products meaning to multiply. So we're going to multiply some things together and then add them all. It'll make sense kind of as we go through this, okay? So what's the purpose of a truth table? All right, it shows how logic design's output can respond to all possible combinations of inputs. All right, so if we have 2 inputs or 3 inputs or 4 inputs, all the different possible combinations. That's why it's very important for us to make sure that we construct them correctly based on the pattern of MSB and LSB and those sort of things, okay? A logic design with n inputs will have 2 to the n combinations. All right, so what's that mean? If we have a logic design that has 2 inputs, input A and input B, all right, we will have 2 squared. 2 to the n, 2 to the 2 is 4. So that means we'll have 4 possible output combinations, okay? If we have 3 inputs, an A, a B, and a C, we will have 2 to the 3rd output combinations, or input combinations, but we'll have that many output combinations. We'll have a total of 8 different output. Now the max that we can do with your breadboard companion is 4. We have 4 inputs, right? Switch 1, 2, 3, and 4. So we can go 2 to the 4th. 2 to the 4th is 16. All right, so what does that mean, 2 to the 4th? All right, 16, we would go 0, 0, 0, 0, all the way up to 1, 1, 1, 1. Okay? And the inputs, they're listed in binary order. So we organize the columns on the left-hand side in counting order. What does that mean? We're going to go 0, 1, 2, 3, 4, 5, 6, 7, which equates to what? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Remember, those all go back and forth. So the first I gave you the 0 through 7, that's in decimal, and then I gave you 0, 0, 0 through 1, 1, 1, that's in binary. So that's what it means that we're counting in binary order. So the inputs will always be in binary order, always starting at 0, okay? The outputs, they're listed in the columns on the far right-hand side, okay? So we'll have our single outputs. So when we build this table, all right, so this is 3 possible inputs, X, Y, and Z, all right, and they are listed out in binary order, right? 0, 0, 0 means 0. 0, 0, 1 means 1. 0, 1, 0 means 2. 0, 1, 1 means 3. And you can see that on the bottom left-hand side, where it says note the binary counting order of the inputs. You will always have your truth table there. So if we continue on, 1, 0, 0 is 4, 1, 0, 1 is 5, 1, 1, 0 is 6, and 1, 1, 1 is 7. I'm equating all of those to their decimal equivalents. So we're counting 0 to 7 in binary using 0, 0, 0, 1, 1, 1. Well, what is 0 to 7? It's 8 digits. 8 digits. 0, 1, 2, 3, 4, 5, 6, 7 is 8 digits. Well, how do we know that? Well, 2 to the 3rd is also 8. So that's how those relate. All right, so this is 3-bit input though, okay? 3 bits that we're inputting here. And then our output table, that's our F1. Okay, those outputs are going to be defined by what we have in our problem or our scenario. So anytime we have a 3-input truth table, yours will always look exactly like this for the inputs. The outputs, that'll always change, but the inputs part of your table will always look like this. All right, so that's constructing a truth table. So then if we have 4 inputs, all right, it's going to be all of these repeated with a 0 in front, and all of these repeated with a 1 in front. So if we take a look at the table, so like I just said, if we had 4 inputs, it's going to look like the table on the right. Now remember, the output varies. So the F2, the F3, the F4 in this table, okay, is going to change based on, you know, the situation that we're going to program or make happen or design. Okay, but the structure is the same and the classification of the inputs. So if we have 2 inputs, 2 to the 2 is 4, there's 4 combinations. So I'm looking at the table on the far left, we have 2 inputs, the inputs are A and B. The only possible combinations we have are 0, 0, 0, 1, 1, 0, 1, 1. Okay, those are the only possible combinations of inputs, and then we'll apply the outputs accordingly. The 3-input table, that's the one we went through on the previous slide together, 0, 0, 0 through 1, 1, 1. So that's 8 possible combination, or 8 digits that we go through. Okay, notice, compare the tables and compare the inputs. The original pattern of the 2-input table, A and B, gets repeated. All right, 0, 0, 0, 1, 1, 0, 1, 1 is always getting repeated. All we do is increment what goes in front of it with a 0 and a 1. So if we go from the 2-input to the 3-input tables, compare. What did we do? We added the 2-input table with a 0 in front and the 2-input table with a 1 in front. That's all we did for the inputs. If we go to the 4-input table, we just took the 3-input table and added zeros in front and 1s in front for every possible combination. So 2 to the 4th is 16. There's 16 possible combinations. But you need to write this table exactly as you see it for the inputs. So if it's 2 inputs, you will see 0, 0, 0, 1, 1, 0, and 1, 1. You will always write it in that order exactly as you see it. Same with the 3-input table. You will write from 0, 0, 0 all the way up to 1, 1, 1. You must put everything in binary order. Same with the 4-input table, 0, 0, 0 all the way up to 1, 1, 1, 1. And it must be written in the exact order that you see it in right now. If you change any of those orders, and I know some of you guys, you've done that in class already, it will not be correct. You must write the table inputs exactly as you see them. Okay, I can't harp on that anymore, but please make sure that you make note of that. Okay, so we want to be able to write our logic expressions. We've done a little bit of this in class already. I've kind of shown you how to do this when we started doing some intro to combo logic. All right, we want to write the minterms. Okay, the minterms are the expressions we get from the outputs when the outputs are true. So we're looking for whenever there's an output of a 1, we can write the minterm associated with it. And then based on all the minterms, we write a sum of products, because the minterms are all multiplied together, or anded together, as we should say. And then we take all of the minterms and we add them up, or we OR them all together. So I want you to start thinking in terms of anding and ORing. So how do we write these minterms? All right, so let's take a look at the truth table we have on the left-hand side. We only care when the output is true, or a 1. Okay? So how do we write that minterm? Well, if we look at the first output, it occurs when x is 0, y is 0, and z is 1. So 0, 0, 1. The way we write those, if we write it, if it's a 0 as an input in our row right there, we write it with a bar over it. So x bar means x is a 0 at that point. Y bar means Y is a 0 at that point. And then Z is a 1, so we don't put a bar over the Z. So if the inputs are zeros, the minterms will have bars on top. If the inputs are a 1, they will not. Okay, and you have to write out each input. So you have to have either X or X bar, Y or Y bar, or Z bar as your minterm for each row. Okay, so let's look at the next possible one. We produce a 1 at 0, 1, 1. When X is 0, Y is 1, and Z is 1. So we will have X bar because X is 0, Y and Z because Y and Z are 1s, so there will be no bar over them. And then we look at the next term. It happens when X is 1, Y is 0, and Z is 0. So 1, 0, 0. So you will get X, Y bar, Z bar. And then the last time that F5, the output is a 1, will be 1, 1, 0. X, Y, Z bar. So hopefully you understand when we write the bar and when we don't write the bar. So if the input's a 1, there's no bar. If the input's a 0, there's a bar over the letter for the input. Okay, so now we've written our 4 minterms. Okay, they're written out there. You can see where they are. Now we write our sum of products. Why sum of products again? Remember, because the first one we have is X bar, Y bar, Z. Those are being ANDed together or multiplying together. Those are a product. Then we have every possible combination of those products, which are the 4 different minterms that we have here. So we're going to OR all those together. So our SOP, our sum of products logic expression, is going to be X bar, Y bar, Z, or X bar, Y, Z, or X, Y bar, Z bar, or X, Y, Z bar. That's our entire expression for the output of that table. Okay? We'll do another example here. So, what I want you to do in your notes, write this table down. All right? Pause the video, see if you can write down all the minterms. And then see, once you write the minterms down, see if you can write the SOP, the sum of products. Alright, so go ahead and do that, and then I'm going to just keep going and go through how we get everything. Okay, so if we take a look, there are 1, 2, 3, 4, 5 terms that I'm going to have where F6 is equal to a 1, where the output is equal to a 1. Alright, so when we see that, that's these 6 terms here. So F6 is a 1 at 0, 0, 0, 1. Or we write that as A bar, B bar, C bar, because all 3 of those are zeros. D. So D is the 1. Then we also get a 1 at A bar, B bar, C, D, right? Because A is 0, B is 0. So that's why it's A bar, B bar. And C is 1 and D is 1, so that's why those are C and D. Okay? Then the next one we have 1, 0, 1, 1. So that equates to A, B bar, C, D. Alright, B is the only one that's a 0 there. That's why it's a B bar. The rest are 1s. So that's why it's A, C, D. Then we have A, B, C bar, D, which equates to 1, 1, 0, 1. Hopefully we're getting the gist of this. You can see the last one, 1, 1, 1, 1 is A, B, C, D. Then we take each one of those minterms that we wrote and we OR them together. Okay, so sum of products. So we write out our final expression as what you see there for F6. I'm not going to read that off. You should be able to see that and kind of see where it came from. Okay, so what we want to do is maybe go the other way. Okay, now we want to create a truth table from a logic expression. So here's the example I'm giving you. Alright, make sure that you pause the video and write all this down. This is a good opportunity for you to do that right now, and then I'm going to explain everything. So I give you F7. F7 is X bar, Y bar, Z bar, or XZ, or X bar, YZ. Alright, now as we go through that, the F7 means that's when those expressions output a 1. So we can see those expressions there. So x bar, y bar, z bar equates to the inputs of 0, 0, 0. And we know that that has to be an output of 1. So in the truth table, we will write a 1 there. We will only write a 1 where all these situations occur. Let's look at another one. We have x bar, y, z. So that we're looking for at 0, 1, 1, there will be an output of a 1. All right, you can see where that lies in the table. And then here's the catch. All right, notice the middle term only has 2 letters. It has x and z. That means we don't care what y is. Y can either be 0 or y can be 1. So that xz actually produces 2 possible scenarios. 1, 0, 1, where y is 0, and 1, 1, 1, where y is 1. So we actually get 4 truths to this table, not just 3. So just remember that that's how that expression is. If one of them is not showing up, it means we don't care. It means it can be a 1 or a 0, and we have to include both scenarios. So very important. So that's how we put a 1 in the truth table there. Okay? Hopefully this is starting to sink in. All right? Let's try one on your own. So what I want you to do is I give you this expression here. We have F8. That's the output. So that happens when we have A, B bar, C, D, or A bar, B bar, or A, B bar, C bar, D bar, or B, C bar, D. Where do you have to be careful on this one? The second Minterm, we don't care if C and D are 0s or 1. And that last Minterm, we don't care if A is a 0 or 1. So make sure that you cover all the scenarios. So how many total inputs are here? There are 4 total inputs. So this means you have to write that big old long table down. So I want you to pause the video and I want you to make that table all the way from 0, 0, 0, 0 up to 1, 1, 1, 1. And I want you to see if you can write all the 1s for the outputs. If it's not a 1, and once you filled in all the 1s, the rest of the terms are 0s. Okay? So let's go ahead and do that. Now, we want to look for A, B bar, C, D. A, B bar, C, D. So you can find it down there. We put a 1 with the output. And then remember I said we have A bar, B bar. We don't care if C is 0 or 1 or D is 0 or 1. So we have to cover 4 different scenarios there. So that's why A bar, B bar. I might refer this, instead of saying A bar, B bar, I might say not A, not B. It means the exact same thing. So I'm going to speak in terms of A bar, B bar, or not A, not B. I want you to get used to understanding that. It means the same thing. So anytime that I have not A and not B, so that means both A and B are 0 at the same time, I will output a 1. So that happens at the first 4 locations in this table. Both A and B are 0s. A bar, B bar, or not A and not B. Okay, let's look at the third Minterm. We have A, not B, not C, not D. So that means we're looking for 1, 0, 0, 0. So if we go down to 1, 0, 0, 0, all right, we'll have a 1 there for the output on the truth table. Then, all right, the last Minterm, we have B, C naught, D, B, C naught, D, which means we don't care if A is a 1 or A is a 0. So we have to have 2 possible scenarios there. But what is important is the 1, 0, 1 portion for the B naught, C, D. All right, and we can see where those other terms lie. It's 0, 1, 0, 1. We put a 1 for the output, and 1, 1, 0, 1 for an output of 1 as well. So now we've completed the truth table based on the SOP logic expression that's been given to us. Okay? So how do we go from, building a design Okay, because you guys are going to have to do something like this. We're going to create the majority vote problem. So you guys are going to create a truth table, and you're going to create a working circuit from it, schematic that you're going to go through and actually, verify that it works in multisim. And then you're going to breadboard your circuit using your breadboard companion, all right, in your breadboard, and show that your circuit works for all of this. All right, so that's going to be one of your major problems after this one that you have to solve. All right, but I'm going to go through a small example for you here. So we want to create a truth table, and we want to create it from design specifications. All right, so first and foremost, when you do this, so this is kind of the steps to building this, we need to identify the number of input variables. So you're going to have to read through a paragraph that I give you, identify the number of input variables, okay? Then you're going to assign variable names and establish the condition for each variable. Okay? Should that can make a true or a false, or a 0 or a 1, or a high or a low. Then we're going to create the truth table. So let's do an example here. We're going to even use something similar to this in the PLC class. So you're going to program a PLC, when you're a senior, to do the same kind of thing here. All right, so we have a large fuel tank that has sensors that monitor temperature and pressure. It says both sensors output a logic low if they are within safe range. All right, so anytime it's safe, the pressure, okay, or temperature is going to output a 0. So that's safe for us, right? If we want an alarm to sound, if either sensor indicates an unsafe condition is present, which means what? If we look at the pressure sensor, 0 means safe, 1 means unsafe. Temperature sensor, 0 is safe, 1 is unsafe. We want the alarm to happen when what? It's true. One of those is true. So when the alarm 1 would be the alarm is on, 0 would mean the alarm is off. So we have to create a truth table here. We have 2 inputs, which means our truth table is only going to consist of 0, 0, 0, 1, 1, 0, and 1, 1. The alarm is our output. So the only time we don't output an alarm is when what? Both sensors are low. Remember, low is 0, high is 1. So if both sensors are low at a 0, 0 state, okay, both sensors are low, 0, 0, the output for the alarm will be 0. We don't want the alarm to go off because everything is in a safe condition. Then we look at the next condition, 0, 1, right? So that's not PT or P bar T. That's going to produce a 1 because what? Temperature is unsafe in that scenario. Our alarm should go off. The next scenario we have is 1, 0. 1 for the pressure. All right, that means pressure is what? Unsafe. We need to output an alarm, so our alarm has to be true there, so our alarm will be a 1. And then in the last scenario, 1, 1, that means our pressure is unsafe and our temperature is unsafe. We must produce an alarm 1. Okay, so this is a basic scenario, all right, in real life of how we control a control system in any sort of place. So where might you find like an alarm like this? We might have, some sort of a refinery type thing where they're refining gas, or a power plant or things like that can go wrong. Even, a Pillsbury bakery or something like that. Or we don't have the right pressure, we don't have the right temperature, things aren't going to, blend together properly, okay? All right, so let's do another example here. All right, so this one's, your teacher keeps her final exams in her office. For security reasons, she would like you to design an alarm system for her office. The office has a window and a door that are equipped with sensors that output a tone when they are secured, which means they are closed. When the alarm system is turned on with a key, the siren should sound if either a window or a door is unsecured. So I want you to try and create the truth table for this on your own first. So pause the video. Remember, what are your input values? How many input values do you have? From there, that's going to drive how large your truth table is. And then when should those be true? So I want you to read through the paragraph. See if you can identify what the inputs are, what the output's going to be. Obviously, the output is a audible alarm, okay? I want you to make sure that you know what the inputs are, all right, and how the inputs drive when the alarm goes off. So pause the video, give this one a shot, okay, and then unpause the video because I'm going to keep just going through here. All right, so when we do this, you should see that the assignments, all right, we have three possible inputs. We have the key, we have the door sensor, and the window sensor, and then we have our alarm, our siren, our audible that's going to go off. Okay, so you should be able to read through the paragraph and identify that we have the window, the door, and the key for this alarm to work. And then you have to design and say what it means for the key. So a 0 for the key means the system is off. A 1 for the key means the system is on. So the only possible way for us to get a siren is what? When the key is a 1. Okay? So anytime that key is a 0, we will not be able to have a siren. So all the sirens are going to be zeros for there. Okay, then we have the door sensor and the possibilities of the door sensor being opened and closed, opened and closed. So what you have to identify here is if we've identified 0 is open, 1 is closed, okay, what's going to drive the alarm? Well, what's going to drive the alarm is what? When the door is open or the window sensor is open. Okay, so our only scenarios are going to happen when the key is in and either what? The door is open, the window is open, or both are open. So let's look at the scenario 1001. Or sorry, 100. The key is a 1, so the system is on. That's good. And then the door is 0, which means it's open. The window is 0, which means it's open. We should have an alarm because the key is in and the door and the window are open, so our siren should go on. Let's look at the next scenario, 101. Well, the key is a 1, so that's good. That means the system is on. Then the door is what? Open because it's a 0. The window is closed because it's a 1. But since the door is open, we will have an alarm. So 101 produces an alarm. Then let's look at the next scenario, 110. The key is in, right? So the alarm is armed. Then we have what? The door is a 1, but the window is a 0. The window is open, so we will have a siren or an alarm. So 110 produces a 1. Let's look at the last scenario. We have the key in, the door is closed, and the window is closed. So we have 111, so there should not be a siren. Everything is on and secure. Alright, so there will be no siren. So we're able to write, our truth table here. There's only 3 possible scenarios where we're going to have an audible. That scenario will be 100, 101, and 110. Alright, so any questions about that, go ahead and ask me in class. Make sure you have good notes. What you might want to do then is, work through this again. So give yourself, back up through this video to where you just see the paragraph. Read through the paragraph and see if you could redesign this system on your own. Like I said, you will have a majority vote problem that I'm going to hand out to you, or it'll be posted online. You're going to have to design it, so you're going to come up with your truth table, and then you're going to have to simulate it in multi-sim, and then you're going to have to breadboard it. Now, we are going to learn some techniques that are going to make that much simpler for you as we move forward, or how to simplify the entire system down. So what I want you to do, you're going to do the majority vote, but we're going to do it in chunks. So you're going to get it all done once. And then I'm going to show you how to simplify it down before you put it before we start breadboarding. Because when you breadboard, I want you to breadboard the most simplified circuit that we come up with. I don't want you to breadboard the big one. It's going to take too long, all right? And there's more opportunity for failure because of getting lost with all the wires and things like that. And it's fairly big. But we're going to learn some techniques in this unit of how to simplify some of those things down. But We're doing well. Like I said, ask me if you have any questions on this. Okay, this will be on your midterm. Obviously, we're going to have a class assignment for it, not just your majority vote problem as well. Okay? All right, guys, as usual, shoot me an email if you got questions or ask questions in class. Else, I will see you guys in class ready to go.